Earth looks solid and familiar on the surface, but nearly 3,000 kilometers below, the planet begins to break the rules. Its outer core moves like a hidden ocean of metal. Its inner core stays solid under impossible pressure. And now, some scientists think the very center of Earth may contain a strange state of matter that behaves like both solid and liquid at once. This is space science, exploring the deepest mysteries of the universe and the worlds beneath our feet. If this kind of deep science fascinates, please like, subscribe, and support the channel. Earth presents a calm face before it reveals anything deeper. From far above, it appears as a round world of blue water, white cloud, brown land, green vegetation, and bright polar ice. Sunlight falls across seas and continents, and the surface seems complete in itself, as if the story ends where rock meets air and ocean meets shore. Yet the surface never rests. The ground shifts by tiny amounts, and, at times, by great ones. Volcanoes open and close. Mountain ranges rise slowly and wear down grain by grain. The seafloor grows in some places and bends downward in others. Warm water issues from cracks in dark volcanic rock far below the waves. A magnetic field surrounds the planet and reaches far into space. All of this belongs to the surface world, but none of it begins there. The visible planet carries signs of a hidden interior, and the first clues appear in ordinary landscapes. Continents spread across the globe in broad, uneven shapes. Some are old and stable, built from rock that preserves a long record of heat, pressure, burial, and uplift. Others hold long belts of younger mountains where the crust folds, breaks, and thickens. Beneath forest soil, river sediment, desert stone, and city ground, the rocky outer shell stores a history of stress and motion. The surface records ancient seas, vanished volcanoes, old impacts, and the closing and opening of oceans. It also records present movement. Sensitive instruments show that points on Earth's surface change position year by year. In many places, the movement is only a few centimeters in a year. Across longer spans, that slow pace becomes immense. Land that seems fixed in daily life turns out to be part of a moving outer layer. The oceans cover most of the planet's surface and give it much of its color from space. Their wide basins do more than hold water. They help regulate temperature, transport heat, dissolve gases, and carry sediment from land toward the deep. Wind stirs the upper waters, while colder and denser water sinks and flows at depth, linking distant parts of the ocean in one broad circulation. Yet the sea does not hide the solid earth beneath it completely. Across the ocean floor run immense mountain chains, deep trenches, broad plains of sediment, and scattered volcanic peaks. These are not random features. They reflect the shape and behavior of the rocky shell below the water. Even where the surface seems smooth, the planet's structure leaves marks. The atmosphere adds another moving layer. It wraps the globe in gases held by gravity and warmed by the sun below and above. Clouds form, drift, and break apart. Storms gather energy over warm water. Rain falls, rivers cut into rock, and ice expands in mountain valleys and polar regions. These surface processes wear down high ground and carry fragments away. Erosion, the slow removal and transport of rock and soil by water, wind, ice, and gravity, reshapes the outer face of the planet. At first, this appears to be a story of weather alone, but it is not. The height of mountains, the distribution of land and sea, the rise of plateaus, and the opening of basins all influence how water moves and where climate leaves its marks. surface weathering and deep planetary structure remain linked, even when the link is not obvious in a single human lifetime. Heat provides another clue. Earth receives energy from the sun, and the surface responds each day and each season. Ground warms in daylight and cools at night. Ocean surfaces absorb light and release heat gradually. Air temperature changes with latitude, altitude, and cloud cover. Beneath these familiar patterns lies a quieter fact. Heat also rises from within the planet. It does not arrive with the sun or with weather. It comes upward through rock from deeper regions. In some places, the evidence is dramatic. Lava pours from volcanic vents. Steam and hot water emerge from geothermal fields. Hot springs rise through cracks and dissolve minerals along the way. In most places, the outward flow of internal heat is much gentler, but it is still measurable. The planet is not a cold shell warmed only from outside. It retains deep heat from its formation and gains additional heat from the decay of radioactive elements in certain rocks. The surface, cool enough for oceans and life, rests over an interior that remains intensely hot. Gravity also speaks quietly of what lies below. Everything at the surface is held close to the planet by the pull of its mass. This pull is not perfectly uniform from place to place. Very small variations reveal differences in the distribution of dense and less dense material inside Earth. A dense mountain route extending downward, a sediment-filled basin, a rising plume of hot rock, or a region of thick cold crust can slightly alter the local strength of gravity. These changes are subtle, but they can be measured. In that way, the surface becomes a place of reading rather than merely seeing. Ordinary ground begins to act like a record of hidden arrangement. Earthquakes bring some of the clearest evidence. At the surface, an earthquake may be felt as shaking, rolling motion, or sudden rupture. Buildings sway, slopes fail, and coastlines can rise or fall. The immediate cause is a release of stored stress in rock. That stress builds because large pieces of the outer shell move relative to one another. Earthquakes are surface events in their effects, but they also serve as signals sent through the planet. Seismic waves. Waves of energy that travel through Earth after a quake, pass downward and across great distances. Some move by compression, pushing and pulling material in the direction of travel. Others move by shear, shaking material from side to side. Their speeds change depending on what they pass through. Some cannot travel through liquids at all. By measuring when these waves arrive and how they bend, reflect, or disappear, researchers learn that Earth is layered. The first hint of the deep interior often begins with the disturbance at the surface. Volcanoes provide a related but different window. A volcano is a place where molten or partly molten rock, gas, and heat reach the surface from below. Not every eruption is large, and not every volcano stays active for long. Some produce broad, gentle flows. Others explode violently when gas expands rapidly. The materials they release matter greatly. Lava, ash, crystals, and gases carry chemical information about the rocks and processes beneath the surface. These materials do not come from one uniform source. Their compositions vary from one setting to another, showing that the interior is not simple or identical everywhere. Even so, each eruption confirms a basic truth. Deep material can rise, change, and emerge into the open air or into the sea. The magnetic field is less visible, yet it belongs to the same pattern of evidence. It guides compass needles and helps shield the atmosphere and surface from charged particles arriving from the sun. The field changes over time. It drifts, weakens in some regions, strengthens in others, and occasionally reverses direction over geological history. Rock at the surface can preserve part of that record. When certain minerals cool, they can align with the magnetic field present at that time. Ancient lava flows and seafloor rocks therefore keep traces of a process that is not created in the crust or atmosphere. Something deep inside Earth must be moving in a way that generates a global magnetic effect. So the surface, even in its calmest scenes, never stands alone. Ocean, continent, atmosphere, gravity, heat, earthquake, volcano, and magnetism all belong to a connected planet. The familiar outer face remains the only part that human feet directly touch. Yet it continuously reveals that it is not self-contained. It is a thin, active boundary where deep causes become visible. The ground under forests and cities, the sea beneath ships, and the air above mountains all carry signs of a planet with structure below the surface. Earth appears quiet only at first glance. Closer observation shows a world whose outer layer is alive with evidence. The ocean floor lies beyond ordinary sight, hidden under kilometers of water, yet it preserves one of the clearest records of Earth's outward motion. From the surface of the sea, little of this appears. Waves reflect light, storms disturb the upper water, and ships pass over great depth with no sign of the solid world below. But mapping of the sea floor reveals a planet marked by long ridges, deep trenches, volcanic arcs, and broad plains. These forms are not scattered at random. They follow large patterns that repeat from one ocean basin to another, and together they show that the outer shell is divided and mobile. At the center of many ocean basins runs a continuous system of undersea mountain chains. This is the global mid-ocean ridge system, a vast belt of elevated sea floor where new oceanic crust forms. In some places the ridge rises steeply, in others it spreads more gently, cut by long fractures that offset one segment from the next. Along the ridge axis, hot material from below rises toward the surface. As pressure decreases, part of this rising mantle rock melts. The melt collects and moves upward, feeding volcanic eruptions beneath the sea. When it cools, it becomes new basaltic crust, dark and dense compared with much continental rock. The ridge is therefore not only a mountain chain, it is a place of construction, where the ocean floor is continually renewed. This renewal leaves a physical and chemical pattern. Rocks nearest the ridge are young. Farther away, the rocks become older. The sea floor also cools as it moves away from the ridge. Hot newly formed crust stands higher because warmth makes it less dense. As it loses heat, it contracts and sinks lower. So the ocean becomes deeper with increasing distance from the ridge. Sediment gathers over time as tiny remains of marine life, dust, volcanic ash, and fragments carried from land settle onto the sea floor. For that reason, the youngest crust near the ridge tends to have less sediment cover, while older crust farther away is buried more deeply. Age, depth, and sediment thickness form a linked pattern across the ocean basins, and the pattern points to steady outward motion. Magnetism adds another layer to the record. When basalt cools from molten rock, minerals that contain iron can align with Earth's magnetic field. That alignment becomes locked into the solid rock. Because Earth's magnetic field has reversed many times in the past, the sea floor preserves alternating bands of magnetic orientation. On either side of a mid-ocean ridge, these bands form a striking mirror pattern. A stripe with one magnetic direction on one side matches a stripe of the same age and direction on the other side. This symmetry is one of the strongest signs that new crust forms at the ridge and then moves outward in both directions. The ocean floor becomes a slowly spreading archive, written in cooling rock. the rate of spreading is not the same everywhere. Some ridges open relatively slowly, producing a rougher and more deeply fractured topography. Others spread faster and create a smoother ridge system with broader volcanic activity. Yet the overall process remains consistent. Heat from deeper within the planet helps drive mantle movement and melting. New crust forms where plates pull apart. As the crust moves away, it cools, thickens, and becomes denser. The ocean floor is therefore not ancient in the same way as much continental crust. Most oceanic crust is geologically young because it is constantly being created and destroyed over long spans of time. The destruction side of the record appears in deep ocean trenches. These long, narrow depressions mark places where old oceanic crust bends downward and sinks back into the mantle. This process is called subduction. The word describes the descent of one tectonic plate beneath another into the deeper earth. Trenches often lie beside chains of volcanic islands or along the edges of continents. The descending plate carries cold rock, water bound in minerals, and layers of sediment downward. As it sinks, pressure and heat alter the minerals inside it. Water released from the slab helps lower the melting point of the overlying mantle, encouraging magma to form. That magma may then rise and feed volcanoes at the surface. In this way, the seafloor record links creation and destruction in one broad cycle. The trenches also mark zones of powerful earthquakes. As one plate bends and descends, stress builds and releases along the boundary. Some earthquakes occur at shallow depth near the trench. Others happen much deeper along the path of the sinking slab. This descending pattern of seismic activity reveals that the plate remains cool and coherent for a long distance beneath the surface. In some regions, earthquakes associated with subduction extend hundreds of kilometers downward. The ocean floor thus provides not only a surface record in rock age and magnetism, but also a dynamic record in the way seismic energy traces moving material into the planet. Transform faults complete the main pattern. These are fractures where plates slide past one another horizontally. Along the mid-ocean ridges, transform faults connect offset ridge segments. Earthquakes cluster along these faults because the motion is not smooth. Stress accumulates as rough rock surfaces resist movement, then releases suddenly. Transform faults show that plate motion is not only a matter of opening and sinking. The outer shell also shears sideways, adjusting to the different directions and rates of spreading across the curved surface of the planet. Hydrothermal systems at the ridge add a more intimate view of the same process. Seawater sinks through cracks in newly formed crust, where it is heated by hot rock below. It reacts chemically with the surrounding minerals and then rises again through vents on the sea floor. Some vents release dark, mineral-rich fluids into the cold ocean, building chimney-like structures round their openings. These systems demonstrate that the ocean floor is active not just in grand tectonic patterns, but also in fine chemical exchange. Heat from the interior alters rock, circulates water, and changes ocean chemistry locally. Life can gather around these vents as well, supported not by sunlight but by chemical energy. Even here, in darkness at great depth, the record of Earth's inner heat remains present. The ocean basins therefore act as a moving map of the planet's outer shell. Their ridges show where crust forms. Their magnetic stripes preserve the rhythm of spreading and reversal. Their trenches show where old crust returns downward. Their earthquakes trace the boundaries and descent of plates. Their vents display ongoing heat exchange between rock and water. None of this can be understood by looking at isolated places alone. The pattern becomes clear only when the seafloor is seen as one connected system that wraps around the globe. From above, The ocean seems to hide the solid Earth. In fact, it helps reveal it. The sea floor preserves motion in a direct way that few continental regions can match, because so much old oceanic crust is replaced before its record becomes too altered or too crowded by later events. In its youth, symmetry, and constant renewal, the ocean floor gives a clean and powerful view of plate tectonics, the theory that Earth's outer shell is broken into moving plates. The hidden floor of the sea becomes a great document of motion, written in basalt, sediment, magnetism, and depth. What appears silent beneath the waves is one of the clearest places where the surface world shows that it is moving over a deeper engine. Continents appear more stable than the ocean floor. Their outlines are familiar, their mountain belts seem permanent, and their wide interiors often feel old beyond measure. Yet continental crust is not simple, and it is not still. It is thicker than most oceanic crust, more varied in composition, and far older in many places. It carries the marks of repeated change. Sediment settles in shallow seas, hardens into stone, and is later buried. Magma rises and cools below the surface or erupts above it. Rocks are pressed, heated, folded, fractured, and lifted. Over immense spans of time, the continents grow, break, collide, and rebuild themselves. Their surfaces preserve this history in broad layers and broken belts. But the deeper structure of the continents reveals even more. Beneath plains, forests, deserts, and mountain ranges, the crust extends downward in uneven thickness, and in some regions it forms deep roots that help support high topography. Continental crust differs from oceanic crust in both material and origin. Oceanic crust is usually dark, rich in iron and magnesium, and formed mainly from basalt at mid-ocean ridges. Continental crust contains more silica and includes many rock types, among them granite, metamorphic rock, volcanic layers, and vast sedimentary sequences. This variety reflects a long and complex history. Continents are assembled through repeated tectonic events. Island arcs may collide with older land. Sediments may accumulate at margins and later be compressed into mountain belts. Magma produced in subduction zones may add new material from below. Fragments of earlier crust may survive several cycles of heating, burial, and uplift. As a result, continental crust is not one uniform shell. It is a layered and patchwork structure, with some parts dating back billions of years and others much younger. Ancient continental cores, often called cratons, are among the most stable parts of Earth's outer shell. A craton is a long-lived block of continental crust that has remained relatively resistant to deformation over great lengths of geological time. These regions tend to lie in the interiors of continents and preserve very old rocks. Their surfaces may look quiet now, but their stones record ancient mountain building, volcanic activity, burial, and erosion over time. The upper expression of those events may wear away, leaving broad plains or low plateaus. Yet deep below, the stability of these old regions depends not only on the crust visible at the surface, but also on colder, thicker material extending downward. This deeper support helps explain why cratons endure. Mountain belts reveal a different side of continental structure. Where plates converge, continental crust may shorten and thicken. Layers of rock fold into large arcs. Faults stack slices of crust on top of one another. Sedimentary basins are squeezed, and granitic bodies may rise from depth, under enough pressure and heat. Minerals change form and new metamorphic rocks develop. At the surface, such regions become chains of peaks, valleys, and plateaus. But mountains are only the visible part of a larger structure. Much like ice floating in water, high topography is often balanced by a deeper extension below. This is sometimes described through isostasy, the tendency of Earth's crust to rise or sink depending on its thickness and density. Thick continental crust can project upward as mountains while also extending downward as a route into the denser material beneath it. These crustal routes are not visible directly, but several lines of evidence reveal them. Seismic waves slow down or speed up depending on the rocks they pass through, and those changes help map crustal thickness. Gravity measurements also indicate where less dense crust reaches deeper than usual. In major mountain belts, the crust may be tens of kilometers thicker than in surrounding regions. The extra thickness helps support elevation, though erosion continually removes material from above. As mountains wear down, the deep root can respond by rising, a process known as isostatic rebound. In this way, the continent adjusts gradually as mass is removed from its surface. The visible landscape and the hidden structure below remain linked over very long spans of time. Sedimentary basins offer another view of continental crust. These broad depressions collect layers of sand, mud, carbonate material, and organic remains over millions of years. Some form where crust stretches and thins. Others develop in front of rising mountain belts, where the weight of the mountains bends the crust downward. In these basins, the surface appears low and quiet, but the crust beneath may hold a great archive of shifting environments, ancient rivers, lakes, shallow seas. And deserts leave distinct layers that build one atop another. Burial compacts the lower layers, and heat slowly alters minerals and organic matter at depth. The existence of such basins shows that continental crust does not only rise into mountains, it can also sag, fracture, and make space for thick accumulations of sediment. Volcanism on continents adds further complexity. Some volcanic regions are linked to subduction, where melting above a descending slab feeds chains of volcanoes near continental margins. Other volcanic provinces arise from extension, where crust thins and allows hot material from below to rise. In still other places, large outpourings of lava cover vast areas, preserving evidence of unusually intense melting events. These different settings produce different rock types and chemical signatures. The continental crust is therefore both a record and a filter. It receives new material from below, mixes it with older crust, and preserves the results in varied forms. Continents are also scarred by faults, some ancient and some active. A fault is a fracture in rock along which movement has occurred. In some regions, faults mark zones where crust has been stretched apart. In others, they record compression or sideways motion, even when inactive for long periods. Faults can remain as zones of weakness that influence later deformation. Rivers may follow them. Earthquakes may return to them. Magma may exploit them as pathways. Through faults, the crust stores memory of past stress and shapes how later events unfold. Despite their apparent permanence, continents are not isolated blocks resting passively at the surface. They move with tectonic plates, collide with one another, separate during rifting, and change thickness through tectonic and thermal processes. Their oldest parts survive not because they are untouched, but because they are supported by deep, buoyant structure, and because they have passed through long intervals of relative stability. Their younger belts, active margins, and sediment-filled interiors show that the continental shell remains dynamic. The surface of a continent can therefore mislead by appearing settled and complete. Under grassland, city, mountain, and basin lies a crust that varies greatly in thickness, density, and history. Some regions hold ancient cores that have endured for billions of years. Others reveal recent tectonic strain, uplift, or subsidence. High mountains are balanced by deep roots. Quiet plains may rest above old collisions or buried rifts. The continents are not merely wide masses of rock above the sea. They are thick, uneven, long-lived parts of the outer shell, built through repeated cycles of addition, deformation, erosion, and adjustment. In their depth and variety, they show that even the planet's most familiar land is only the outer expression of a far more structured interior. Below the continents and oceans, the rocky outer shell does not continue unchanged. At a certain depth, seismic waves begin to behave differently, and this change reveals one of the most important boundaries in the planet's outer structure. This boundary is called the Mohorovičić discontinuity, often shortened in science to the MOHO. Though the longer name explains it more fully, it is the zone where the crust gives way to the mantle below. The crust and the uppermost mantle are both solid rock, yet they differ in composition, density, and the speed at which seismic waves travel through them. The boundary is not marked by empty space or by a gap. It is a transition from one kind of rocky material to another, and its presence is known chiefly through the behavior of waves released by earthquakes. The discovery of this boundary begins not in deep drilling, but in careful listening. When an earthquake occurs, energy travels outward through the planet in several forms. Some waves move through compression, and some move through side-to-side shearing. As these waves pass through different materials, their speeds change. They may bend, reflect, or split into new paths. Early seismologists noticed that some waves arrived sooner than expected at distant stations. This could be explained if part of the energy had travelled through a deeper layer where the waves moved faster. From this pattern, they inferred that a distinct boundary must separate the shallower crust from a denser region below. That deeper region is the mantle, and the boundary between the two is the Mohorovičić discontinuity. The crust above this boundary is chemically and physically different from the mantle beneath it. Continental crust tends to contain more silica-rich rock such as granite, and many metamorphic and sedimentary varieties. Oceanic crust is usually darker and denser, built mainly from basalt and related rock. Beneath both lies mantle rock rich in minerals formed from magnesium, iron, silicon, and oxygen. One common mantle rock is peridotite, a dense ultramafic rock dominated by olivine and pyroxene. These minerals allow seismic waves to travel faster than they do through most crustal rocks. The difference in wave speed is therefore a sign of real material contrast. It is not simply a matter of greater pressure at depth, though pressure also increases there. The boundary marks a change in what the planet is made of. The depth of this discontinuity varies widely. Under ocean basins, where the crust is relatively thin, the boundary may lie only a few kilometers below the sea floor. Under continents, it usually lies much deeper. Beneath major mountain belts, it can descend far farther still because the crust there is thickened by tectonic compression. This variation makes the boundary uneven on a global scale. It rises beneath young oceanic regions and sinks beneath ancient continents and active mountain ranges. The planet's outer structure is therefore not a smooth shell of constant thickness. It is a varied outer layer resting on a denser rocky interior. Even though the MOHO is a major boundary, it is not always a simple, sharp line everywhere. In some places, especially where the crust has been strongly deformed or altered, the transition may occur across a thicker zone rather than at one exact depth. Certain rocks from the lower crust can gradually change in composition and density until they begin to resemble upper mantle material more closely. In other cases, mantle rock may be altered by fluids and partial melting, especially in tectonically active areas. These complexities mean that the Mohorovičić discontinuity is best understood as a seismic and material boundary whose exact expression can vary from place to place. Observations indicate a clear global contrast between crust and mantle, but the fine details remain regionally complex. Direct contact with this boundary is extremely rare. Human drilling has penetrated only a small fraction of the crust. The deepest boreholes remain far above the mantle in most locations. For this reason, most knowledge of the Moho comes indirectly through seismic studies, gravity measurements, laboratory work on rocks, and occasional natural exposures. In a few regions, sections of mantle rock have been brought to the surface by tectonic processes or volcanic activity. These rocks, called mantle xenoliths when carried upward in magma, or exposed periddotites in certain tectonic settings, offer partial insight into what lies below the crust. Yet they do not replace the broad planetary picture that seismology provides. The boundary itself remains mostly beyond direct reach. The existence of this discontinuity changes how the surface world is understood. The crust is not merely the top part of a uniform rocky globe. It is a distinct outer skin, chemically different from the deeper material below. It has formed through special processes such as melting, crystallization, sedimentation, metamorphism, and tectonic assembly. The mantle, by contrast, represents a larger and more continuous reservoir of denser rock. The Moho is therefore not only a line on a seismic model, it marks the point where Earth's familiar crust ends and a more massive interior begins. This boundary also matters for the way heat and stress move through the planet. The crust stores radioactive elements that contribute to heat production, especially in many continental rocks. The mantle below carries heat upward and can deform over long periods, though it remains solid overall. The contrast between crust and mantle influences how tectonic plates behave, how magma forms, and how seismic waves are guided through the outer Earth. A thick crust may insulate deeper heat differently than a thin one. A crust cut by faults may transmit stress and fluids in ways unlike a stable continental block. In every case, the crust-mantle boundary helps define the base of the region in which surface geology takes place. The oceans make this boundary especially striking. Beneath a thin blanket of marine sediment and a relatively thin oceanic crust, the mantle lies much closer to the surface than it does beneath continents. In some places, tectonic processes even expose mantle rocks at or near the sea floor. This closeness reminds the observer that Earth's deeper structure is not uniformly remote. Under certain parts of the planet, the transition from crust to mantle occurs within a depth range that is small compared with the full size of Earth. Yet even there, it remains part of a system too deep for ordinary experience and known mainly through careful measurement. The Mohorovičić discontinuity is thus a threshold of understanding. Above it lies the diverse crust, with its continents, basins, mountains, and sea floor. At it, seismic waves announce a change in density and composition. Below it begins the upper mantle, a region of hotter and denser rock that belongs to a different scale of planetary behavior. The boundary does not shine or gape open. It is silent, buried, and unreachable to daily life. Yet each earthquake that sends waves through Earth helps trace it again. Through those waves, the crust is revealed as a limited outer layer rather than the whole of the rocky planet. The surface world gives way, at the Moho, to a deeper and more uniform interior that supports everything above it. Below the Mohorovičić discontinuity, the upper mantle begins as a vast region of solid rock, It lies beyond direct human reach, yet it is not beyond understanding. Seismic waves pass through it. Rare samples from volcanic eruptions carry fragments of it upward. Laboratory experiments recreate some of its pressure and temperature conditions. Together, these lines of evidence show that the upper mantle is not molten in the ordinary sense. It is made mostly of rock that remains solid even under intense heat. This fact can seem surprising at first, because the upper mantle is hot enough to challenge common ideas about stone. In daily life, heat is associated with softening, melting, and collapse. In the deep earth, heat acts alongside immense pressure, and the result is different. The upper mantle remains mostly solid because pressure raises the temperature required for widespread melting. The rocks in this region differ from the crust above. They are denser and richer in magnesium and iron. One of the most important upper mantle rocks is peridotite, a coarse-grained rock dominated by the minerals olivine and pyroxene. Olivine is a greenish mineral when seen in hand sample, though in the deep earth its colour is irrelevant in the darkness and pressure below. It matters because its crystal structure and chemical composition strongly influence how the upper mantle behaves. Pyroxenes and other minerals share that role. Together they create a rock that can transmit seismic waves efficiently and remain mechanically strong over short timescales, even while changing shape over very long ones. Temperature rises with depth in the upper mantle, but not in a simple or uniform way. Heat comes upward from deeper parts of the planet, while the overlying lithosphere, the rigid outer shell made of crust and the uppermost mantle, conducts heat more directly toward the surface. In some regions, the upper mantle is relatively cool, especially beneath old oceanic plates or ancient continental interiors. In other regions, it is warmer, such as beneath spreading centers, volcanic settings, or tectonically active areas. Pressure also rises steadily with depth, and that pressure becomes one of the defining conditions of this region. It compacts mineral structures, changes density, and keeps most mantle rock solid even where temperatures are extremely high by surface standards. The word solid, however, needs care. In ordinary speech, a solid is something fixed in shape, hard to deform, and resistant to flow. Upper mantle rock is solid in the sense that its minerals remain in a crystalline structure rather than existing as a liquid, yet over immense spans of time it can deform. A crystal lattice is the orderly arrangement of atoms in a mineral. Under stress, defects in that lattice can move, grain boundaries can shift, individual crystals can rotate, stretch, and recrystallize. These slow changes allow solid rock to alter its shape without breaking all at once. So the upper mantle is not fluid like water, but neither is it permanently rigid like cold iron in everyday use. It is a hot solid capable of gradual deformation. This behavior matters because Earth is not static. Heat moves upward from the interior, and the planet must release that heat over time. In the upper mantle, one of the important ways this happens is through slow, solid-state flow. Solid-state flow means movement that occurs while the material remains solid. It is not a contradiction, though it sounds like one at first. A useful comparison comes from ice in a glacier. Ice is solid, yet a glacier can creep downslope over long periods. Mantle rock behaves in a somewhat similar way under its own conditions of stress, heat, and time. The comparison is limited, because the materials and conditions are very different, but it helps clarify the idea. The upper mantle does not need to melt completely in order to move. Seismic waves offer powerful evidence for this region's nature. Compression waves and shear waves both pass through the upper mantle, which confirms that it is solid enough to transmit both types. Shear waves, in particular, cannot move through true liquids. Their passage through most of the upper mantle shows that this region is not a global magma ocean. At the same time, the speeds of these waves vary from place to place. Colder regions usually transmit them faster because colder rock is stiffer. Warmer regions often slow them somewhat. These differences allow scientists to build broad images of temperature and structure within the mantle. The upper mantle thus appears not as a featureless shell, but as a varied region shaped by heat, composition, and motion. Rare volcanic eruptions provide more direct clues. Some magmas rise quickly enough to carry pieces of mantle rock to the surface before those pieces can fully react or melt. These fragments, called xenoliths, act as samples from depth. They often consist of peridotite and preserve minerals formed in upper mantle conditions. Their textures record deformation. Some crystals are stretched or aligned, showing that the rock has experienced directed stress while remaining solid. Others reveal partial melting or chemical alteration in specific settings. These samples do not represent every part of the upper mantle, but they confirm the general picture from seismology and experiment. The upper mantle is a region of hot, dense, mostly solid rock that changes slowly under pressure. Laboratory studies deepen that picture. Researchers place mantle minerals under high pressure and temperature, then measure how they deform and how quickly seismic waves travel through them. These experiments cannot perfectly reproduce the full scale and duration of deep earth processes, but they allow a controlled look at the behavior of mantle materials. Results indicate that temperature, grain size, water content, and stress all affect how easily upper mantle rock deforms. Even small amounts of water bound within minerals can weaken certain rocks, not by filling open spaces like ordinary groundwater, but by changing how defects move through crystals. This is one reason the upper mantle is understood not as a simple block of stone, but as a complex solid whose mechanical behavior depends on conditions. The upper mantle also plays a central role in linking the surface plates to the deeper planet. The rigid lithosphere includes only its uppermost part. Beneath that rigid layer, upper mantle rock becomes less resistant to slow deformation. It still transmits seismic waves as a solid, yet it can accommodate motion over geological time. This distinction helps explain how tectonic plates move across Earth's surface without requiring the whole outer planet to break or melt. The upper mantle supports, resists, and gradually yields, depending on depth, temperature, and timescale. So this region challenges ordinary intuition. Stone at the surface is cool, brittle, and often still. Stone in the upper mantle is hot, compressed, and capable of slow change while remaining solid. It stores heat, transmits seismic energy, and deforms over spans so long that motion becomes visible only through its consequences. Mountains rise, plates shift, and volcanic systems form because this deep solid rock does not behave like the rock of a cliff face or road cut. The upper mantle remains a world of minerals under conditions far beyond surface experience, yet its basic lesson is clear. Deep inside Earth, solidity does not mean immobility. It means ordered matter enduring heat and pressure while slowly, steadily changing shape. Beneath the rigid outer shell, the upper mantle enters a region that behaves differently. This zone is often called the asthenosphere. The term refers to a weaker part of the upper mantle that lies below the lithosphere, the strong outer layer made of crust and uppermost mantle. Weak here does not mean fragile or easily broken in the ordinary sense. It means less resistant to slow deformation over long spans of time. The rock remains mostly solid. Seismic waves still pass through it. Yet compared with the colder and stiffer material above, it yields more readily under stress. This difference is essential for the movement of tectonic plates, because the plates form part of the rigid lithosphere and travel over a deeper region that can slowly adjust. The asthenosphere is not identified by sight because no direct view exists. It is inferred from several kinds of evidence, especially seismic observations and the behavior of the surface plates. One important clue comes from the way some seismic waves travel more slowly through certain depth ranges in the upper mantle. This region is sometimes described as a low-velocity zone, meaning that the speed of seismic waves drops relative to the layers above. The slowdown does not mean the rock has turned into a great underground sea of melt. Instead, it suggests that the material is hotter, somewhat less rigid, and in some places may contain a very small fraction of partial melt or other features that reduce its stiffness. Observations indicate that temperature plays a leading role, while the exact contribution of melt, water, and grain scale processes can vary by region, and remains an active subject of study. Heat is central to the nature of the asthenosphere. As depth increases below the lithosphere, temperature rises to levels where mantle rock approaches the conditions at which it becomes easier to deform. Pressure is also greater there, and pressure helps keep the material solid. The result is a state in which the minerals still hold a crystalline structure, but that structure can change more easily under long-lasting stress. Atoms do not break free into a full liquid. Instead, defects move through crystals, grain boundaries shift, and the rock can slowly flow. This flow is extremely slow by human standards, but over millions of years it becomes enough to support the movement of continents and oceanic plates across the globe. The contrast between lithosphere and asthenosphere is therefore a contrast in mechanical behavior more than a simple contrast in composition. The rocks may be broadly similar in chemical makeup, especially where both are made largely of peridotitic mantle material. What changes most is how that material responds to temperature and stress. The lithosphere is cooler and stronger. It can bend, fracture, and store stress over long intervals before releasing it in earthquakes. The asthenosphere is hotter and less rigid. It does not store and release stress in quite the same way, because it can accommodate slow deformation more continuously. This mechanical contrast gives the outer shell of Earth its ability to move as large plates rather than as one unbroken skin. The lower boundary of the lithosphere is not always sharp. In some places, especially beneath old continents, the strong outer layer extends much deeper than beneath young oceanic crust. Oceanic lithosphere forms hot at mid-ocean ridges and thickens as it cools with age. So the top of the asthenosphere tends to lie deeper beneath older ocean basins than beneath younger ones. Beneath ancient continental interiors, the rigid mantle part of the lithosphere can be very thick and cold, creating a broad, stable route. In tectonically active regions, by contrast, the lithosphere may be thinner, bringing the weaker asthenospheric material closer to the surface. This means the asthenosphere is not a perfectly even shell surrounding the planet at one uniform depth. It is a global zone with regional differences in depth, temperature, and properties. Water, though scarce by surface standards, may also influence this region. In the deep mantle, water is not present as open liquid filling cracks in the ordinary way. Instead, small amounts of hydrogen can be held within mineral structures. This chemically bound water can weaken minerals by affecting how easily defects move through their crystal lattices. Under some conditions, it may help mantle rock deform more readily. Even a modest amount can matter. Yet the degree to which water contributes to the asthenosphere's weakness varies among studies and settings. Temperature remains the most widely accepted control. While water is often understood as an important additional factor rather than a universal explanation by itself. Partial melt is another possibility, but it must be treated carefully. In some places beneath ridges or tectonically active regions, tiny amounts of melt may exist between mineral grains. This melt can reduce rigidity and affect seismic wave speeds. However, the asthenosphere is not generally understood as a broad layer of mostly molten material. It remains a solid region with perhaps a small percentage of melt in certain areas. This distinction matters because the ability of plates to move does not require a global liquid layer beneath them. It requires only that the rock below the rigid lithosphere be capable of slow, continuous deformation. The motion supported by the asthenosphere is not motion of the asthenosphere alone. It is part of a larger mantle system in which heat and material move over immense spans of time. Still, at this depth, the effect on the surface becomes easier to understand. A rigid plate can travel because the material beneath it does not have to break in the same way. It can creep and adjust. When oceanic lithosphere bends into a trench, deeper mantle material can flow in response. When plates spread apart at a ridge, hot mantle rises from below and contributes to the creation of new crust. The asthenosphere therefore acts as a zone of accommodation where deep heat and solid-state flow allow surface tectonics to operate. Seismic studies also reveal that this region is not identical in all directions. In some places, waves travel at slightly different speeds depending on their direction of movement. This property, called anisotropy, often reflects the alignment of minerals during flow. If mantle rock deforms over long periods, crystals such as olivine can become preferentially oriented. Their alignment then influences how waves pass through the rock. Such measurements provide a subtle but important clue that deformation in the asthenosphere is real and organized, not random. The rock records motion in its very fabric. So the asthenosphere is neither a molten ocean nor a simple rigid stone layer. It is a deep zone of hot, mostly solid mantle that is weak enough to flow slowly and strong enough to remain crystalline. It lies beneath the outer shell and helps make plate tectonics possible. Through temperature, pressure, mineral behavior, and time, it creates a middle condition between brittleness and melt. The surface world does not feel this region directly, yet mountains, oceans, trenches, ridges, and drifting continents all depend on its quiet yielding. In the upper mantle, the asthenosphere marks a change from the rigid outer shell to a deeper form of motion, where stone remains solid and still learns to move. Deeper within the upper mantle, the rock enters a pressure range where familiar minerals can no longer keep the same internal arrangement. This region is called the mantle transition zone. It lies roughly between 410 kilometers and 660 kilometers below the surface, though the exact depths can vary somewhat with temperature. Here the material is still mostly made from the same major chemical ingredients that dominate the upper mantle above. What changes is the crystal structure, the orderly internal arrangement of atoms inside the minerals. Pressure grows so strong in this depth range that minerals are forced into denser forms. The transition zone is therefore not defined mainly by a change in overall chemistry. It is defined by pressure reorganizing matter. In the shallower upper mantle, one of the most important minerals is olivine. It is abundant and strongly influences how mantle rock behaves. As pressure increases with depth, olivine eventually becomes unstable in its familiar form. Around the top of the transition zone, it changes into a denser mineral called wadsleyite, deeper still, with more pressure. Wadsleyite changes into ringwoodite, another denser form of the same basic composition. These are called polymorphs, which means minerals with the same chemical formula but different crystal structures. This idea is central to the transition zone. The atoms do not need to belong to a new substance in order for the mineral to become a new phase. A phase is a distinct structural state of matter under given conditions. In this region, pressure alone can force one phase to become another. These mineral changes are not small details hidden inside individual crystals. They affect the properties of vast regions of the mantle. When a mineral becomes denser, seismic waves usually travel through it differently. Density, elasticity, and wave speed all change together. For this reason, the top and bottom of the transition zone are recognized globally as seismic discontinuities, boundaries where waves reflect, refract, or change speed in clear ways. The discontinuity near 410 kilometers is associated mainly with the transformation of olivine into wadsleyite. The deeper discontinuity near 520 kilometers is often linked to the change from wadsleyite to ringwoodite, though this signal is not always equally sharp everywhere. At the bottom of the transition zone near 660 kilometers, ringwoodite breaks down into still denser minerals stable in the lower mantle. Together, these changes make the transition zone one of the clearest mineralogical layers inside Earth. Pressure is the main reason these transformations occur, but temperature matters too. In colder mantle material, the depths of the boundaries can shift. In warmer mantle, they can shift in the opposite direction. This happens because phase changes depend on both pressure and temperature. As a result, the transition zone is not a perfectly flat shell of fixed thickness around the entire planet. Seismic studies show that its boundaries can rise or sink slightly depending on regional conditions. Cold descending slabs in subduction zones may push the upper boundary shallower and the lower boundary deeper, thickening the transition zone locally. Warmer regions may narrow it. These variations turn the transition zone into more than a static layer. It becomes a sensitive record of temperature and motion inside the mantle. The minerals themselves also matter because they store water differently from the minerals above. In the deep earth, water is not usually present as ordinary liquid filling large open spaces. Instead, hydrogen can be incorporated into mineral structures. Wadsleyite and ringwoodite are especially important because their crystal structures can hold much more of this bound water than olivine above them. This does not mean the whole transition zone is uniformly saturated. Observations indicate that some parts may be relatively dry, while other regions, especially where subducted material carries water downward, may store much more. It remains uncertain how evenly water is distributed across the whole transition zone. What is clear is that these minerals have the capacity to act as major reservoirs within the deep water cycle of the planet. This ability changes how the transition zone is understood. It is not simply a passage through which mantle rock descends and rises unchanged. The zone can trap, release, and redistribute water depending on the minerals present and the temperature conditions around them. Water held in minerals can influence melting, density, electrical conductivity, and mechanical behavior. In some studies, the transition zone appears to act partly as a storage region, slowing the movement of water deeper into the mantle. In others, regional complexity is emphasized, with wetter and drier patches reflecting the long history of plate descent and mantle circulation. The broad picture remains that this zone is mineralogically unusual because of how pressure-created crystal structures interact with hydrogen. The transformation of minerals in this region also affects the movement of sinking slabs. When old oceanic lithosphere descends into the mantle at subduction zones, it enters the transition zone carrying its own temperature structure and mineral history. As the minerals inside the slab transform, density changes can help pull the slab downward. At the same time, The phase boundaries may alter how easily material crosses into deeper regions. In some cases, slabs appear to slow, flatten, or pond within the transition zone before sinking farther. Hot rising material may also be influenced by these boundaries. The transition zone is therefore not just a passive depth interval. Its mineral transformations can shape the physical path of mantle flow. Deep earthquakes add another sign of the zone's special nature. Most earthquakes occur in the shallow crust, where brittle failure is common. Yet some earthquakes happen much deeper, especially in cold subducting slabs that penetrate the transition zone. One proposed reason involves the rapid transformation of olivine into denser phases under stress. If a mineral changes structure suddenly enough, it may weaken the surrounding rock or concentrate strain. Observations support a connection between deep seismicity and mineral transformations in cold slabs, but the exact mechanism remains under study. What matters here is that the transition zone is one of the few parts of the deep mantle where such transformations can strongly affect the behavior of descending rock. Laboratory experiments are essential in understanding all of this. Researchers recreate the extreme pressures and temperatures of the transition zone using special presses and heated cells. In these conditions, they observe when olivine changes to wadsleyite, when wadsleyite changes to ringwoodite, and how much water these minerals can store. They measure density, elasticity, conductivity, and deformation. These results are then compared with seismic observations from the real Earth. No laboratory can reproduce the full scale and complexity of the mantle, but the agreement between high-pressure mineral physics and seismic data gives strong support to the basic model of the transition zone as a region defined by phase change. So the transition zone is a place where pressure writes its influence directly into stone. The rock remains solid, yet its minerals are not fixed in one permanent form. Olivine becomes wadsleyite. Wadsleyite becomes ringwoodite. The same basic chemistry is packed into tighter structures, and those structures alter density, wave speed, and water storage. Seismic boundaries mark these changes on a planetary scale. Subducting slabs and rising mantle currents respond to them. Water may gather within them in significant amounts, though not uniformly everywhere. In this depth range, matter is not replaced so much as rearranged. The transition zone stands as a deep mineral region, where the familiar materials of the upper mantle are pressed into new internal order by the weight of the world above. Below the transition zone, the mantle enters a broader and heavier region known as the lower mantle. This is the deepest and largest part of the rocky mantle, extending from about 660 kilometers beneath the surface to the boundary of the core far below. Here pressure becomes far greater than in the regions above, and temperature continues to rise. The rock remains solid, yet its minerals have been transformed into forms stable under these deeper conditions. The lower mantle is not a separate world in composition from the mantle above in the broadest sense. It is still made mainly of oxygen, magnesium, silicon, and iron, with smaller amounts of other elements. What changes is the structure of the minerals, their density, and the way the rock behaves under extreme pressure. At the top of the lower mantle, the ringwoodite of the transition zone becomes unstable. It breaks down into a new set of minerals. The most important of these is a dense silicate structure called bridgmanite, which is the most abundant mineral in Earth by volume. Alongside it appears ferropericlase, a magnesium iron oxide that also contributes to the physical properties of the deep mantle. These minerals are denser than those above and are arranged in ways that allow them to remain stable under immense compression. The transition at about 660 kilometers is therefore a major boundary not only in seismic behavior, but also in mineral identity. Above it, The mantle holds one family of crystal structures. Below it, the lower mantle begins with another. This region is vast. It occupies far more depth than the upper mantle and transition zone combined, because of its size. The lower mantle contains a large portion of Earth's rocky mass and plays a central role in transporting heat upward from the deep interior. Heat does not remain fixed at depth. Over geological time, it moves outward. Some of that heat comes from the early formation of the planet, preserved in the deep interior since Earth assembled and differentiated. Some also comes from radioactive decay in the mantle and crust, though the crust contains a larger share of certain heat-producing elements. The lower mantle participates in the long release of this internal energy. It does so not through widespread melting, but mainly through slow convection. Convection is the transfer of heat by movement within a material. In liquids, it can be seen in boiling water, where warmer fluid rises and cooler fluid sinks. In the mantle, the process is far slower and takes place in solid rock that deforms over immense spans of time. Warmer mantle material becomes slightly less dense and tends to rise. Cooler material becomes relatively denser and tends to sink. These motions are slow, measured in centimeters per year rather than in the rapid speeds seen in air or water currents. Yet across millions of years, they become powerful enough to shape the thermal evolution of the planet. In the lower mantle, convection is one of the main ways Earth sheds deep heat. The lower mantle does not flow like a simple, uniform fluid. Its movement is constrained by pressure, mineral structure, temperature, and viscosity. Viscosity is a measure of resistance to flow. A material with high viscosity resists deformation more strongly than one with low viscosity. Lower mantle rock has a very high viscosity compared with ordinary liquids, but it still convects because the timescales are so long and the driving forces act persistently. Temperature differences, the pull of sinking slabs, and the buoyancy of warmer rising material all contribute. The exact viscosity of the lower mantle varies with depth and region, and this affects how quickly material can circulate. Seismic waves reveal much about this region. Compression waves and shear waves both pass through the lower mantle, showing again that it remains solid. Their speeds generally increase with depth because pressure makes the material denser and stiffer. Yet the increase is not perfectly smooth everywhere. There are regions where waves move faster or slower than average, indicating colder or warmer material, or perhaps differences in composition. These variations allow researchers to build seismic images of the lower mantle, much as medical scans use differences in wave or radiation behavior to reveal structure inside the body. The resulting picture is not one of stillness. It is one of broad thermal and structural variation within a deep solid shell. One of the clearest signs of movement comes from subducting slabs. When old oceanic lithosphere sinks at trenches, it can descend through the upper mantle and into the lower mantle. Seismic imaging often shows cold, relatively fast regions extending downward from known subduction zones. In some cases, these slab-like structures penetrate well into the lower mantle. This indicates that the deep mantle is linked to the plate motion seen at the surface. The lower mantle is not isolated from the shallower world. It receives material from above, and that material may carry cold temperatures and chemical differences downward with it. At the same time, warmer material can rise from depth. Some of this rising mantle may contribute to volcanic hotspots at the surface, though the exact paths and origins of such upwellings remain subjects of study. What is well supported is that the lower mantle is involved in upward transfer of heat, and that some parts of it are warmer and more buoyant than others. These temperature differences drive slow circulation. The rock does not need to melt fully in order to rise or sink. Small changes in density are enough when the whole process acts over such enormous volumes and long durations. Pressure in the lower mantle also influences how minerals deform. Under these conditions, the crystal structures of bridgemanite and related minerals govern the mechanical behavior of the rock. Experiments and models suggest that lower mantle minerals may deform differently from those in the upper mantle, and this affects how convection proceeds. Grain size, temperature, and chemical variation all matter. So the lower mantle is not simply a deeper version of the upper mantle. It is a region with its own mineral framework and its own style of resistance and motion. Though mostly inaccessible, the lower mantle leaves indirect effects at the surface. Its temperature structure can influence the rise of mantle plumes, the sinking of slabs, and the overall rate at which heat escapes from the planet. Over long spans of time, this affects volcanic activity, plate motion, and the cooling history of Earth as a whole. The lower mantle therefore belongs to the deep engine of the planet, not as a fiery liquid chamber, but as a massive solid region through which heat and material move slowly. So this part of Earth is defined by scale, pressure, and persistence. It is a realm where the mineral forms of the mantle have changed into denser arrangements, where bridgemanite dominates, and where solid rock still circulates under the force of heat and gravity. The lower mantle holds a large share of Earth's mass and carries energy upward through slow convection. Seismic waves show it to be structured rather than uniform. Sinking slabs and rising warm regions reveal that it is active rather than still. In the long descent from surface to core, the lower mantle marks a vast interval where pressure has remade the minerals and where the deep planet continues its quiet, steady movement. Near the base of the mantle, the deep Earth becomes more irregular. The broad patterns of the lower mantle remain, but the rock above the core is not uniform in temperature, wave speed, or perhaps even composition. This lowermost mantle region, often called the D-double prime layer, lies directly above the core mantle boundary. It is thin compared with the full depth of the mantle, yet it is one of the most complex parts of the whole planet. Here heat rises from the core below into the rocky mantle above. Sinking slabs from the surface may arrive after a long descent. Mineral structures may change again under extreme conditions. Seismic waves passing through this region often behave in unusual ways, showing that the base of the mantle contains large structures, sharp contrasts, and smaller pockets of especially strange material. One of the clearest features seen in seismic studies is the presence of two immense slow-wave regions deep in the mantle, one mainly beneath Africa and one beneath the Pacific. These are often called large low-shear velocity provinces because shear waves move more slowly through them than through the surrounding mantle. Their scale is enormous. They rise upward from near the core mantle boundary for great vertical distances and spread across broad parts of the deep mantle. They are among the largest structures inside the planet, yet their exact nature remains uncertain. Observations clearly show that they are seismically distinct from surrounding mantle. It remains uncertain whether they are mainly hotter than average, compositionally different, or both at once. Temperature alone can slow seismic waves, because hotter rock is generally less stiff. A hotter deep mantle region would therefore be expected to reduce wave speeds. But composition also matters. If a region contains a different mixture of minerals, more iron, recycled oceanic crust, or other long-lived chemical differences, waves may slow for reasons beyond heat alone. Many models suggest that the large slow-wave provinces are thermochemical structures, meaning that both heat and composition contribute to their behavior. This idea helps explain why they may be stable over long spans of time rather than mixing away quickly. Even so, the balance between temperature and composition remains actively studied. The structures are observed. Their full origin and internal makeup are not yet settled. These deep provinces matter because they help shape mantle flow. Warmer, buoyant material may rise from their margins or tops, while colder slabs descending from subduction zones may gather around them or between them. In some models, the edges of these provinces are places where deep mantle plumes begin. A mantle plume is a broad upwelling of unusually hot mantle material that may rise toward the surface and contribute to hotspot volcanism. Observations support a connection between some surface hotspots and the edges of deep mantle slow-wave regions, but the paths from the lowermost mantle to the surface are difficult to trace in full detail. What is well established is that the base of the mantle is not a flat, even thermal blanket. It is a region of strong lateral contrast. Above and around thus large provinces lie other structures as well. Some areas of the lowermost mantle show relatively fast seismic wave speeds, often interpreted as colder material. These may represent old subducted slabs that have sunk to great depth. If so, the base of the mantle becomes a meeting ground between descending cold material from the surface and rising heat from the core below. This contrast can create sharp boundaries and complicated patterns of flow. The deepest mantle is therefore both a thermal boundary layer and a place where Earth's long internal circulation may concentrate its most dramatic differences. Very close to the core mantle boundary, even smaller and stranger features appear. Some seismic studies detect zones where wave speeds drop far more strongly than in the broad, slow-wave provinces. These are called ultra-low velocity zones. They're much smaller than the giant provinces, but their seismic effect can be extreme. In these zones, shear waves may slow so much that the material seems very different from ordinary mantle rock. One possible explanation is partial melt, meaning a small fraction of liquid mixed into otherwise solid material. Another possibility is an unusual iron-rich composition, or chemically distinct material that has collected near the base of the mantle. Observations indicate that such zones exist in several places, but their exact composition and origin remain uncertain. The double prime layer also seems to include a mineral change. Under the pressures and temperatures near the base of the mantle, bridgmanite may transform into a different crystal structure known as post-perovskite. This phase is thought to become stable only under the most extreme conditions of the lowermost mantle. Its presence can affect seismic anisotropy, wave speed, and the way deep mantle rock deforms. Anisotropy means that waves travel differently depending on direction, often because minerals are aligned by flow. In the lowermost mantle, this directional behavior appears in some regions and suggests organized deformation near the core. The possible presence of post-perovskite helps explain part of that pattern, though the exact distribution of this mineral phase within the deep mantle remains tied to local temperature and chemistry. Heat flow across the core mantle boundary is one of the defining features of this region. The liquid outer core below is hotter than the mantle above, so heat moves upward into the base of the mantle. This heat may help drive convection in both layers, though in very different materials and styles. The amount of heat crossing the boundary is not known with complete precision, but it is large enough to matter for the evolution of the core, the mantle, and the magnetic field generated deeper below. Where the mantle is colder above the boundary, heat may escape from the core more efficiently. Where the mantle is hotter, the transfer may differ. So the uneven structure of the lowermost mantle influences not only the mantle itself, but also the thermal life of the core. Because the deepest mantle is known mainly through seismic waves and mineral physics, its picture remains incomplete. Seismic images depend on where earthquakes occur and where waves are recorded. Some parts of the deep earth are sampled better than others. Small structures may be missed or blurred. Temperature and composition can produce similar seismic effects, making interpretation difficult. For these reasons, the deep mantle is described with confidence in some broad features and with caution in others. The giant slow-wave provinces are strongly supported. Ultra-low velocity zones are increasingly well documented in many places. The exact chemistry, buoyancy, and history of these structures remain open questions. So the deepest mantle above the core is a region of contrast and concentration. Broad, slow-wave provinces rise from its base beneath Africa and the Pacific. Smaller, ultra-low velocity zones cluster in places near the boundary itself. Cold slab material may reach this depth from far above. New mineral phases may appear where pressure and temperature are greatest. Heat from the core enters the mantle here, and the structure of the rock controls how that heat moves on. The lower mantle above is already deep and powerful, but near its base the planet grows more uneven. The quiet descent through dense rock arrives at a boundary layer where seismic waves slow. Mineral order shifts, and the deep earth reveals some of its largest and most enigmatic internal forms. At the base of the mantle, the rocky earth meets a very different interior. This meeting place is the core mantle boundary, one of the sharpest and most consequential boundaries inside the planet. Above it lies solid, silicate rock, shaped by immense pressure and long, slow convection. Below it lies the liquid outer core, a metallic layer dominated by iron and nickel, and carrying some lighter elements as well. The contrast between these two regions is extreme. Density changes abruptly. Composition changes abruptly. Seismic behavior changes abruptly. Temperature remains very high on both sides, yet the materials respond in entirely different ways. The core mantle boundary is therefore not merely a change in depth, it is a change in the fundamental character of the deep earth. This boundary lies about 2,900 kilometers beneath the surface. At that depth, pressure is immense, and temperatures are high enough to challenge the stability of almost any familiar surface material. Yet pressure alone does not determine the state of matter. What matters is the combination of pressure, temperature, and composition. The mantle above remains solid because its silicate minerals are stable under those conditions. The core below is liquid because metallic iron alloy at that depth and temperature does not remain fully solid there. This difference is revealed clearly by seismic waves. Compression waves can pass through both solids and liquids, though their speeds change. Shear waves cannot travel through liquids. When earthquakes send waves through Earth, shear waves disappear from paths that require passage through the outer core. That disappearance is one of the strongest signs that the outer core is liquid. The core mantle boundary also marks a large jump in density. The lower mantle is dense rock, but the liquid core beneath it is denser still. This affects how seismic waves bend and reflect when they encounter the boundary. Some waves pass through into the core as compression waves and return altered. Others reflect from the boundary itself. By studying these paths carefully, researchers infer not only the existence of the boundary, but also details about its topography and complexity. It is not a perfectly smooth surface on all scales. In some places it may be irregular, with relief created by thermal and chemical interaction between mantle and core. Some parts may be hotter or cooler than others. Some may be chemically altered by exchanges across the boundary over long spans of time. Heat flow is one of the defining processes here. The core is hotter than the mantle above it, so heat moves upward across the boundary. This transfer matters for both layers. In the mantle, it can help generate buoyant upwellings and influence deep convection. In the core, the loss of heat helps drive the motion of a liquid metal, which in turn sustains Earth's magnetic field. The exact amount of heat crossing the boundary is not known with complete certainty, but it is central to the history of Earth's interior. If the heat flow is high in a particular region, the mantle there may warm from below more strongly. If it is lower in another region, the pattern of deep convection may differ. The uneven mantle structures just above the boundary therefore affect how the core cools, and the state of the core affects how the mantle receives deep heat. The relationship is two-sided and ongoing. Chemical interaction may also occur at this boundary. The mantle is made mostly of silicate minerals, while the core is metallic, yet over billions of years. Some exchange of elements may take place under such extreme conditions. Iron from the core may react with materials at the base of the mantle. Light elements from the core may partition in complex ways. Mantle material may partially melt where it is heated strongly from below. Some of the strange seismic features seen just above the boundary, such as ultra-low velocity zones, may reflect products of this interaction. Observations indicate that small, localized regions near the boundary behave very differently from ordinary mantle rock. It remains uncertain whether these zones are best explained by partial melt, unusual composition, or some combination of both. What is clear is that the boundary is not chemically simple. The thermal contrast across the core mantle boundary also produces a boundary layer in the mantle above. A boundary layer is a region where properties change rapidly over a relatively short distance. Near the base of the mantle, temperature may rise steeply because of heat entering from the core. That extra heat can lower the stiffness of the rock, influence mineral stability, and help create the complex seismic structures of the D-double prime layer. At the same time, the liquid core below may be affected by how efficiently the mantle removes heat from different areas. Cold descending slabs that reach the base of the mantle can increase heat extraction locally. Hotter deep mantle provinces may reduce it. In this way, the irregular structure of the lowermost mantle above the boundary helps shape the dynamics of the fluid metal below. The boundary is also important because it separates two very different styles of motion. In the mantle, even deep solid rock deforms slowly over immense timescales. In the outer core, liquid metal can circulate much more readily. This fluid motion is still shaped by pressure, temperature, rotation, and magnetic forces, but it belongs to a different physical regime. The core mantle boundary is where slow, solid-state convection gives way to metallic fluid motion. No other major interior boundary combines such a strong contrast in material type and dynamical behavior. Seismic studies continue to refine the picture. Certain wave phases skim along or reflect from the boundary and provide clues to its small-scale structure. In some regions, the boundary seems especially sharp. In others, it may be accompanied by thin, anomalous layers. The interpretation of these observations is difficult because wave behavior depends on temperature, composition, topography, and phase state all at once. Still, the overall conclusion remains secure. The base of the mantle is not merely another gradual deepening of the same rock. It is the edge of the metallic core. This deep divide also helps place the whole outer to inner journey in perspective. From the surface down to this point, Earth remains a rocky planet. Crust, upper mantle, transition zone, lower mantle, and deep mantle all differ greatly, but they belong to one broad, silicate shell. At the core mantle boundary, that continuity ends. The region below is not another kind of rock. It is a global layer of liquid metal, the planet's deepest heat, its magnetic field generation. and the later story of the inner core all depend on that fact. So the core mantle boundary stands as the great interior divide. It is a buried interface where solid silicate Earth meets fluid metallic Earth. Seismic waves announce its presence through sharp changes in speed and by the loss of shear transmission into the core. Heat crosses it from below and helps organize the thermal life of the deep planet. Chemistry may become complex along it. Strange small structures gather near it. Above it, the mantle carries heat in slow-moving solid rock. Below it begins a hidden ocean of metal. At this depth, Earth changes from rocky world to metallic world, and the boundary between them governs both. Below the core mantle boundary begins the outer core, a vast layer of liquid metal hidden beneath nearly 3,000 kilometers of rock. It extends downward for more than 2,000 kilometers before reaching the solid inner core. This region cannot be seen directly, yet its basic nature is among the best established features of the deep Earth. Seismic waves, Earth's magnetic field, laboratory studies of iron under pressure, and models of planetary evolution all point to the same conclusion. The outer core is a fluid layer composed mainly of iron, with nickel and smaller amounts of lighter elements mixed into it. In this hidden metallic ocean, motion never fully stops. The liquid moves, heat escapes, and electrical currents flow. From these motions comes one of the most important protections of the surface world, the global magnetic field. The evidence for a liquid outer core begins with earthquakes. When an earthquake sends seismic waves through Earth, compression waves can cross both solids and liquids, but shear waves cannot pass through liquids. Across large parts of the globe, stations do not receive shear waves that would have had to cross the core. Instead, those waves are absent, creating what is known as a shadow zone. Compression waves also change speed and direction sharply when they enter the core, producing their own pattern of delayed arrivals and shadowed regions. These observations together reveal a fluid layer beneath the mantle. This conclusion does not depend on one single earthquake or one single station. It emerges from a consistent global pattern repeated many times. The composition of the outer core is understood in broad outline, though not in complete detail. Iron is the dominant ingredient, and nickel is also present, as expected from the chemistry of planetary formation and from comparisons with certain meteorites. Yet pure iron alone does not fully match the density of the outer core inferred from seismic data. The liquid appears slightly less dense than pure iron under the same conditions. This indicates the presence of lighter elements mixed into the metal. Candidates include sulfur, oxygen, silicon, carbon, and hydrogen. Observations and experiments support the presence of some combination of lighter elements, but it remains uncertain exactly which mix dominates and how that mix varies with depth. What is clear is that the outer core is not chemically pure. It is an iron-rich alloy with additional light components. Conditions in this region are extreme. Pressure is immense, though still lower than in the solid inner core below. Temperature is also extremely high, high enough to keep the metallic alloy liquid at these depths. The balance between pressure and temperature is essential. Greater pressure tends to favor solidity by forcing atoms closer together, but higher temperature tends to favor fluid motion by increasing atomic energy. In the outer core, the temperature remains above the melting point of the local alloy, so the metal stays liquid. Deeper down, conditions change enough for the inner core to exist as a solid. Here, however, the metal flows. This fluid motion is not random stirring. It is organized by heat, buoyancy, Earth's rotation, and the electrical conductivity of the liquid metal. Electrical conductivity means the ability of a material to carry electric current. Liquid iron under core conditions is highly conductive. When such a fluid moves, it can generate and sustain magnetic fields through a process known as the geodynamo. A dynamo is a system in which motion in an electrically conducting fluid converts kinetic energy, the energy of motion, into magnetic energy. In Earth, the outer core is the fluid layer where this happens. The geodynamo does not require the whole outer core to move at one speed or in one simple direction. In fact, the flow is thought to be complex. Earth's rotation helps organize it into columns or spiraling patterns aligned broadly with the rotation axis. Heat escaping from deeper regions and chemical buoyancy associated with inner core growth both help drive convection in the liquid metal. Convection in the outer core differs from mantle convection because the material is liquid and metallic rather than solid rock. It can move more readily, though still under the influence of enormous pressure and rotation. These motions produce electrical currents, and the currents help maintain the magnetic field that extends outward into space. The magnetic field generated in the outer core reaches far beyond the deep interior. At the surface, it guides compasses and influences charged particles from the sun. Farther out, it helps create the magnetosphere, the region of space dominated by Earth's magnetic field. This shield reduces the direct impact of solar wind on the upper atmosphere. The field is not perfectly constant. It drifts and changes over time. The magnetic poles wander. Field strength rises and falls in different regions. Over long geological intervals, the polarity reverses, meaning the magnetic north and south positions exchange places. These changes indicate that the underlying flow in the outer core is dynamic and evolving. The outer core is therefore not only a deep fluid layer, it is the physical source of a planet-wide effect. Without its moving conductive metal, Earth would not have the same long-lived global magnetic shield. This does not mean the surface would become impossible in every respect, but the conditions for atmosphere, radiation exposure, and space weather interaction would be significantly different. The quiet surface world depends in part on motion within this hidden metallic layer. Seismic observations also hint that the outer core may not be perfectly uniform. Wave speeds vary subtly, and the topmost outer core may have some stratification, meaning layering produced by differences in temperature or composition. Some models suggest that lighter material may accumulate near the top of the core, creating a stable layer where vertical mixing is reduced. Other studies emphasize ongoing turbulence and complex interaction with the mantle above. Observations indicate that some form of structure may exist near the top of the outer core, but its thickness, stability, and exact cause remain uncertain. Even within this great fluid shell, order and layering may appear. At its lower boundary, the outer core meets the solid inner core. At its upper boundary, it touches the rocky mantle. Between those two interfaces, the liquid metal carries heat outward and participates in the gradual cooling of the planet. As Earth loses internal heat over geological time, conditions in the core change as well. The growth of the inner core, which occurs as liquid metal freezes onto the solid center, affects the outer core by releasing both latent heat and light elements into the surrounding fluid. These buoyancy sources help sustain convection. Thus, the outer core is linked upward to the mantle and downward to the inner core. It is a middle metallic region, liquid yet enclosed, dynamic yet hidden. So the outer core can be understood as a deep ocean of iron-rich metal beneath the rocky earth. Seismic waves prove its fluid state. Density measurements imply that lighter elements are mixed into the iron and nickel. High temperature keeps it liquid, while pressure, rotation, and buoyancy organize its motion. That motion drives the geodynamo and sustains the magnetic field that surrounds the planet. Subtle layering may exist within it, and its behavior is shaped by both the mantle above and the inner core below. In this region, the planet is no longer rock at all, but moving metal, carrying heat and current through darkness under unimaginable weight. Within the liquid outer core there is no visible shoreline and no quiet line marked in stone. Yet at great depth, a boundary appears where the metal changes state. This is the inner core boundary, the surface of the solid center, enclosed by the surrounding liquid iron-rich alloy. It is one of the most subtle and important interfaces inside Earth. Above it, the outer core remains fluid and convex. Below it, the inner core exists as a solid sphere. The transition between the two is not caused by a change from one major substance to another. Both regions are dominated by iron with nickel and lighter elements mixed in. What changes is the balance between temperature, pressure, and composition. At this depth, pressure has become so great that the iron-rich alloy can exist as a solid, even though the temperature remains extraordinarily high. This boundary is therefore a freezing front deep inside the planet. The word freezing must be understood in the special conditions of the core. It does not resemble the quiet surface freezing of water in winter air. In the core, the material is metallic, the pressure is immense, and the temperatures are measured in thousands of degrees. Yet the underlying idea remains the same. A liquid cools enough, under local conditions, for solid crystals to form and persist. Earth's inner core grows because the planet gradually loses heat over time. As the core cools, the pressure and temperature conditions at the center favor solidification. Liquid metal becomes solid at the boundary, and the solid region slowly expands outward. This growth is not only a matter of temperature. Composition matters as well. The liquid outer core is not made of pure iron. It contains lighter elements mixed into the metal. When iron-rich solid forms at the inner core boundary, those light elements do not fit equally well into the solid structure. Many of them are excluded from the growing solid and remain preferentially in the surrounding liquid. This process is called partitioning, meaning that different elements distribute themselves differently between solid and liquid phases. The newly formed inner core becomes more iron-rich than the liquid around it, while the adjacent outer core becomes relatively enriched in lighter material. That lighter liquid is more buoyant, and its release helps drive convection in the outer core. So the inner core boundary is both a thermal and a chemical frontier. As solidification proceeds, latent heat is released. Latent heat is energy given off during a change of phase without an immediate drop in temperature. At the same time, the exclusion of lighter elements generates compositional buoyancy in the liquid outer core. These two effects together provide important energy sources for outer core motion, and therefore for the geodynamo that maintains Earth's magnetic field. The boundary is not merely the edge of the inner core. It is an active interface where growth of the solid center helps sustain motion in the fluid shell around it. The exact way solidification occurs at this boundary remains difficult to observe directly. So much of the understanding comes from seismic waves and high-pressure experiments. Seismic studies show that waves reflect from and pass through the inner core boundary in ways that confirm a sharp contrast between liquid and solid material. Some waves speed up after entering the inner core, while others reflect from the boundary and return information about its roughness and local structure. These measurements indicate that the boundary is globally coherent, but not perfectly simple. In some places it may be sharper, in others it may include fine-scale layering, topography, or small transition zones shaped by local thermal and chemical conditions. Small-scale layered structures near the boundary have been proposed from seismic observations. These may reflect variations in how crystallization proceeds, how light elements concentrate in the liquid just above the solid surface, or how local melting and refreezing modify the interface. Observations indicate that the outermost part of the inner core may differ from deeper inner core material in seismic properties. It remains uncertain whether this difference is caused mainly by crystal size, by preferred alignment of iron crystals, by chemical variation, or by deformation at the boundary itself. What is clear is that the interface is not a perfectly uniform surface with identical conditions everywhere. Melting may also occur locally, even while the inner core grows overall. This is another reason the boundary is scientifically rich. The long-term trend favors growth of the solid inner core as Earth cools, but local variations in heat flow and fluid motion can complicate the picture. If one region of the core boundary loses heat more efficiently, solidification may be favored there. If another region receives different thermal or compositional conditions, remelting may occur. In this way, the inner core boundary may be a place of simultaneous freezing and melting in different regions, even though the net effect through geological time is expansion of the solid center. Observations and models support this possibility, but the full geographic pattern remains uncertain. The texture of the newly formed inner core depends on the crystal structure adopted by iron alloy under these conditions. For many years, the dominant view has been that iron in the inner core mainly takes a hexagonal, close-packed form, though other structures remain under discussion in some studies, especially when lighter elements are included. Whatever the exact phase relations, the way crystals nucleate and grow at the boundary matters. If crystals align preferentially or deform soon after forming, they can influence the speed of seismic waves traveling in different directions. This is one reason the inner core boundary is closely tied to the broader puzzle of inner core anisotropy, the directional dependence of seismic wave speed inside the solid center. The boundary may also record the history of inner core growth. If the solid center begins forming later than once assumed, it may have grown relatively quickly afterward. Some seismic studies suggest that the outermost inner core differs from deeper layers, perhaps reflecting changing growth conditions through time. Other observations indicate soft or deformable behavior in the outermost part of the inner core, which may point to recent crystallization, partial textural disorder, or interaction with flow in the liquid outer core. These results do not overturn the basic picture of a solid inner core growing within a liquid outer core. Instead, they show that the boundary preserves memory of how that growth has proceeded. Because no direct sample exists from this depth, uncertainty remains inevitable. The precise mix of light elements in the outer and inner core is still debated. The amount of local melting along the boundary is not fully resolved. The fine-scale shape and roughness of the interface vary among studies and may differ from place to place, yet the larger picture is strong. The inner core boundary is the place where liquid metal becomes solid metal under extreme pressure. In doing so, it releases heat and rejects lighter elements, both of which help power the outer core's motion. So this buried interface can be understood as a living edge within the deep planet. It marks the surface of the inner core, but it does more than separate liquid from solid. It is a place of crystallization, buoyancy release, latent heat production, and seismic contrast. It may freeze unevenly. It may melt in places even as it grows overall. It may shape the texture of the solid center from its very first crystals outward, at the heart of the metallic earth. The inner core boundary is where the hidden ocean begins to become a hidden sphere. At the center of the planet lies the inner core, a solid sphere enclosed on all sides by the liquid outer core. It is small compared with the whole Earth, yet it carries unusual importance because it exists under the most extreme pressure found anywhere in the planet. Temperature there is also extraordinarily high, comparable to the surface of the Sun in broad order of magnitude. Yet the inner core remains solid because pressure rises enough to force the iron-rich alloy into a stable crystalline state. This alone makes the inner core remarkable. In ordinary experience, heat softens matter and leads toward melting. At Earth's centre, heat and pressure act together, and pressure wins. The deepest metal does not remain liquid. It becomes a compressed solid sphere. The inner core is understood mainly through seismic waves. No direct sample can come from such depth, and no borehole can approach it. Yet waves from earthquakes cross the planet and interact with the solid centre in measurable ways. Compression waves travel faster through the inner core than through the liquid outer core around it, which is consistent with the transition from fluid to solid. Normal modes, the global vibrations set ringing by large earthquakes, also support the presence of a solid centre. Over time, these observations have turned the inner core from an inference into one of the best established parts of Earth's deep structure. It is not guessed at loosely. It is detected repeatedly by the behaviour of the planet itself when it vibrates. Its composition is thought to be dominated by iron, with nickel also present and probably a small amount of lighter elements mixed into the alloy. The exact identity and amount of those lighter elements remain uncertain. Candidates include sulfur, silicon, carbon, oxygen, and hydrogen. What matters for the basic picture is that the inner core is not a perfect ball of chemically pure iron. It is an iron-rich alloy under conditions that cannot be matched exactly on planetary scale in the laboratory, even if many of its essential properties can be studied in smaller experiments. This mixture, together with pressure and temperature, governs the density, sound speed, crystal structure, and deformation of the inner core. For many years, the inner core was described in simple terms as a solid metal sphere, and that description remains true at the broadest level. Yet the closer it is examined, the less simple it appears. Seismic waves do not move through it equally in all directions. This property is called anisotropy. In plain terms, it means that the inner core seems easier for certain seismic waves to cross along some directions than along others, most often. Waves travelling roughly parallel to Earth's rotation axis are observed to move faster than waves travelling in equatorial directions. This pattern has been recognised for decades and is one of the most important clues to the inner core's internal organisation. Anisotropy suggests that the solid metal inside the inner core is not arranged randomly. If crystals of iron alloy become aligned in preferred directions, seismic waves can travel differently depending on their path. Deformation during growth, flow within the solid, or preferred crystallization at the inner core boundary may all help produce this alignment. Observations indicate that anisotropy exists, but its exact pattern remains debated. Some models suggest that it changes with depth. Some propose that the innermost part of the inner core differs from the outer part. Others infer that the direction of fastest wave travel may tilt or vary regionally, rather than pointing everywhere in one simple way. The existence of inner core anisotropy is widely supported. Its full geometry and cause remain uncertain. This complexity has led to the idea that the inner core may itself contain layers or domains. In some studies, the deepest central region appears distinct enough to be described as an innermost inner core, meaning a central part with a different anisotropic pattern or crystal arrangement from the rest of the solid sphere. This does not imply a separate major layer in the same sense as mantle and core. It implies a structural difference within the solid inner core itself. perhaps recording a change in growth style, crystal alignment, or thermal history through geological time. Observations support the possibility of internal heterogeneity, but the size, shape, and exact nature of any such inner domain remain under discussion. The outermost part of the inner core has drawn special attention in recent years because it may behave less rigidly than once assumed. Seismic studies indicate that the outer shell of the inner core may be softer or more deformable than the deeper interior. This does not mean it is liquid. The inner core remains solid overall. Instead, it suggests that the newest solid near the boundary may have a different texture, smaller crystal size, more disorder, or greater ease of deformation under stress. Some studies also suggest that this outermost region may change shape slightly over time as it interacts with flow in the surrounding liquid outer core. Observations support unusual behavior in the outermost inner core, while the exact mechanism remains uncertain. That possible softness matters because it changes the way solidity is imagined at the center of the planet. A solid sphere need not be equally rigid in every part. Under great pressure and temperature, solid metal can still deform slowly, especially over immense spans of time. The deeper interior may be more strongly compacted and more stably organized, while the outermost solid shell may be younger, more texturally complex, and more responsive to forces imposed by the fluid around it. In this way, the inner core begins to resemble earlier deep regions of Earth where the simple categories of hard and soft, fixed and flowing, become less clear. At the center, solidity remains real, but it is not simple stillness. The crystal structure of iron in the inner core plays a central role in these ideas. Many experiments and calculations support a hexagonal close-packed structure for iron under inner core conditions. Though the presence of light elements may alter details, different crystal structures transmit seismic waves differently and respond to stress in different ways. If crystals grow with preferred orientation, or later become aligned by deformation, anisotropy follows naturally. Recent mineral physics studies also explore how chemical stratification, growth history, and thermal conductivity might create depth-dependent patterns in inner core structure. These models do not yet yield one final agreed picture, but they reinforce the idea that the inner core records a long physical history rather than existing as a simple frozen lump. The inner core may also move slightly relative to the mantle and crust above, though this topic must be described carefully. Some studies interpret repeated seismic observations as evidence that the inner core's rotation rate can differ a little from that of the rest of the planet over time. Other studies emphasize that changes in the outermost inner core's shape or texture can mimic part of that signal. Observations indicate that the inner core is dynamically connected to the fluid outer core and does not behave as a perfectly isolated rigid body. It remains uncertain how much of the observed variation reflects rotation, deformation, or both together. So the solid inner core is best understood as a dense iron-rich center under unimaginable pressure. Solid overall, yet internally structured and possibly changing. Seismic waves show that it is not isotropic and not uniform. Its crystals may align. Its deepest part may differ from its outer part. Its outermost shell may be softer and more deformable than older views assumed. All of this means that the center of Earth is not a dead, motionless kernel. It is a solid metallic sphere whose internal order carries the marks of growth, pressure, heat, and slow interaction with the fluid world around it. To understand matter at the center of Earth, observation alone is not enough. Seismic waves reveal that the inner core is solid, that it is structured, and that it behaves in ways not fully explained by a simple, uniform sphere of iron. But seismic waves do not show atoms directly. They do not reveal crystal structures by themselves, and they do not settle every question about which light elements are present, or how those elements move under such extreme conditions. For that, researchers turn to mineral physics, the study of how materials behave under high pressure and temperature, and to high-performance simulations that follow atoms in motion. In this region of inquiry, the solid inner core becomes not only a seismic object, but also a physical problem of iron, alloying, phase stability, diffusion, and elasticity under the most extreme conditions found in any part of the planet. The first challenge is simple to state and difficult to solve. What form does iron take at inner core pressure and temperature? Pressure at the center is immense, and temperature is high enough that ordinary experience offers no useful guide. Under these conditions, iron can arrange itself into different crystal structures. A crystal structure is the repeated internal pattern in which atoms are packed. For many years, the leading model has been hexagonal close-packed iron, often described as the most likely structure under inner core conditions. This form remains widely supported because it fits many experimental and theoretical results, yet it is not the only possibility considered. Some studies indicate that cubic structures may become competitive under certain conditions, especially when nickel and light elements are included. The current picture is therefore firm in broad terms and open in detail. Iron at the center is solid and crystalline, but the exact stable arrangement may depend on composition as well as pressure and temperature. This matters because crystal structure influences seismic behavior. Different structures transmit sound at different speeds and in different directions. If the inner core is anisotropic, then its atomic arrangement and crystal alignment become central to the explanation. A crystal whose elastic properties differ with direction can make seismic waves travel faster along one path than another. If many such crystals align over large distances, the whole inner core can acquire directional behavior. Mineral physics therefore provides one of the key bridges between atomic-scale matter and planet-scale seismology. The problem is not only which phase of iron is stable, but how that phase grows, deforms, and aligns. Light elements complicate this picture further. The core is not thought to be made of pure iron and nickel alone. Seismic density and cosmochemical reasoning both indicate that lighter elements must be present, yet their exact identity and abundance remain uncertain. Silicon, sulfur, oxygen, carbon, and hydrogen are all considered possible contributors, and different combinations may operate in the outer and inner core. These elements matter because even a small fraction can alter density, melting behavior, crystal stability, and wave speed. They also affect how material partitions between liquid outer core and solid inner core at the freezing front. When mineral physics addresses the inner core, it is therefore studying not only iron itself but iron alloy under extreme conditions. Experiments that approach these conditions use devices capable of compressing tiny samples to enormous pressures while heating them to thousands of degrees. In some cases, powerful lasers provide the heat. In others, shock methods produce extreme conditions for brief moments. X-ray techniques then probe how atoms are arranged and how the material responds. These experiments are technically demanding because the sample sizes are tiny, the temperature gradients may be large, and the relevant conditions are close to the limit of what can be sustained and measured. Even so, they provide valuable information. They show which crystal phases can appear, how melting temperatures shift, and how alloys behave when light elements are present. No experiment reproduces the full inner core in all its size, time scale, and complexity, but together they constrain what is physically plausible. Simulations extend this work. First principles calculations and molecular dynamics models allow researchers to examine how atoms move under core conditions, how crystal phases compete, and how elastic properties change with temperature and composition. These methods do not replace experiment or seismology, they complement them. A simulation can test whether a proposed phase of iron alloy would match the observed density and seismic velocity of the inner core. It can explore whether hydrogen, oxygen, or carbon would remain fixed in place within a solid lattice, or move more freely. It can examine how nickel changes the phase diagram, the map of which crystal forms remain stable under different pressures and temperatures. In recent work, such calculations have reinforced the idea that the inner core may be more complex than a single, perfectly ordered solid iron phase. One especially important line of study concerns diffusion. Diffusion is the gradual movement of atoms or ions through a material. In an ordinary solid at surface conditions, atoms are often thought of as largely fixed in place except for vibration. Under inner core conditions, that assumption may not fully hold for light elements. Simulations indicate that in some iron alloys, hydrogen, oxygen, or carbon may become highly mobile even while the iron lattice remains solid. This means the heavy iron framework could preserve solid crystalline order, while some lighter components move through it much more freely. Such behavior blurs the ordinary boundary between solid and liquid categories. It does not make the whole inner core molten, but it suggests that not every part of the material behaves like a standard rigid solid. This possibility has drawn attention because it may help explain puzzling seismic observations. The outermost inner core appears to be softer or less rigid than expected in some studies. Traditional solid iron phases do not always reproduce the full seismic pattern under realistic temperature conditions. If light elements become mobile within a solid iron structure, the effective mechanical behavior of the material may change, its seismic velocities, attenuation, and directional properties may differ from those of a fully ordinary solid alloy. Some researchers therefore propose that unusual states of matter may exist under inner core conditions, especially in regions where temperature, pressure, and composition favor strong mobility of light elements. At the same time, caution remains necessary. Laboratory and computational studies do not yet yield one final answer. Some support hexagonal close-packed iron as the main inner core phase. Others suggest that cubic or short-range ordered structures could better match some seismic properties. Some models favor hydrogen and silicon as key light elements. Others allow different mixtures. Some explain anisotropy mainly through crystal alignment and deformation. Others invoke thermal or chemical heterogeneity. The broad lesson from mineral physics is not that one mystery has already been fully solved. It is that the inner core cannot be treated as a simple ball of pure, static iron. Even the thermal history of the inner core enters this picture. How and when the inner core began to nucleate, meaning when solid crystals first formed at the center, depends on the core's composition and cooling history. Some recent work suggests that spontaneous nucleation of a solid inner core requires more supercooling than may have been available in some earlier models. This makes the onset of inner core growth an active research topic. The age of the inner core, the way crystals first appeared, and the changing composition of the surrounding liquid all influence what material state should be expected today. The present inner core carries the consequences of that long history. So the study of matter under core conditions turns the solid center into a laboratory of extremes. Iron alloy must be understood not in ordinary categories, but under crushing pressure, enormous heat, and with light elements that may change both structure and motion. Experiments compress and heat tiny samples. Simulations follow atoms through dense metallic lattices. Seismic observations test whether the predicted properties match the real Earth. Together they show a solid center that is physically real but materially subtle. The inner core is iron-rich, yet not pure. It is crystalline, yet not necessarily uniform. It is solid, yet may permit unusual mobility among its lighter ingredients. At this depth, physics itself must be pushed to unusual limits in order to explain what the deepest metal is actually doing. At the center of Earth, the idea of a solid inner core meets a new possibility. Observations and experiments agree that the inner core is solid overall, composed mainly of iron alloy under immense pressure and high temperature. Yet some of its properties do not fit comfortably within the behavior expected from an ordinary solid metal. Seismic waves suggest that parts of the inner core may be softer than predicted. The outermost region appears less rigid in some measurements. The behavior of light elements within the iron lattice may not match the stillness associated with a conventional crystalline solid. These signs have led to a proposal that the inner core, or parts of it, may exist in a state that lies between familiar categories. This state is often described as superionic. A superionic state is one in which part of the material remains fixed in a solid lattice, while another part moves more freely, almost as if it were in a liquid. In the context of Earth's inner core, the heavy iron atoms would maintain a crystalline structure, forming a stable framework under pressure. At the same time, lighter elements such as hydrogen, oxygen, or carbon might move through that framework with much greater mobility than expected in a typical solid. The material would not be fully liquid, because the iron lattice would remain intact. It would not be fully solid in the traditional sense, because some components would not be fixed in place. It would be a mixed state, combining structural order with internal motion. This idea arises from both experimental work and theoretical studies. High-pressure experiments and atomic simulations suggest that under inner core conditions, certain light elements can become highly mobile within iron alloys. The energy of the system, shaped by extreme temperature and pressure, allows these smaller atoms to move between positions in the crystal lattice without destroying the overall structure. In such a case, the iron atoms would define the shape and strength of the solid, while the lighter elements would contribute to a different kind of internal behavior. This is not a simple extension of ordinary solid or liquid categories. It is a distinct state that appears only under extreme conditions. The concept of a superionic state is not unique to Earth. It has been studied in other materials and has been proposed for the interiors of certain icy planets and moons, where water under high pressure may enter a similar condition. In those settings, oxygen atoms may form a lattice while hydrogen ions move freely. In Earth's inner core, the focus shifts to metallic systems. The iron lattice would take the role of the fixed framework, and light elements would provide the mobile component. The analogy helps clarify the idea, but the materials and conditions are different. The inner core is a metallic environment, not an icy one, and its behavior must be understood in its own terms. Seismic observations provide part of the motivation for considering this possibility. The speed of waves through the inner core and the way those speeds vary with direction suggest a material that is not perfectly rigid. The outermost inner core in particular appears to have lower shear strength than might be expected for a simple solid iron alloy under those conditions. Traditional models can explain some of this behavior through crystal alignment, temperature variation, or partial textural disorder. Yet they do not always account for all observations at once. A superionic model offers an additional way to interpret the data, especially if mobile light elements reduce the effective rigidity of the material while leaving the overall structure intact. At the same time, this proposal remains an area of active research rather than settled fact. Observations indicate unusual properties in the inner core, but they do not directly show atoms moving within a lattice. Experiments approach core conditions but cannot perfectly reproduce them. Simulations depend on assumptions about composition and interactions that are still being refined. Some studies support the possibility of supersonic behavior in iron alloys under inner core conditions. Others find that more conventional solid phases, with different crystal structures or alignment patterns, can explain the data without invoking a distinct supersonic state. It remains uncertain whether the inner core truly exists in such a state, whether only certain regions do, or whether the observed properties can be explained in other ways. The role of light elements is central in this question. If elements such as hydrogen or oxygen are present in sufficient amounts and under the right conditions, their mobility could change the mechanical and thermal properties of the inner core. If they are present in smaller amounts or bound more tightly within the lattice, their effect may be limited. Determining the composition of the inner core is therefore one of the key challenges. Seismic data constrain density and wave speed, but multiple combinations of elements can produce similar bulk properties. Mineral physics experiments and simulations narrow the possibilities, but do not yet yield a single definitive composition. The question of a supersonic state is closely tied to this uncertainty. Another important factor is temperature. The inner core is hot, but the exact temperature profile is not known with complete precision. If temperatures in certain regions approach conditions where light elements become more mobile, then a supersonic-like behavior becomes more plausible. If temperatures are lower relative to the stability of the lattice, then conventional solid behavior may dominate. The balance between temperature and pressure is delicate. Even small differences can influence which phases are stable and how atoms move within them. The idea of a supersonic inner core also connects to the history of the planet. The inner core has grown over time as the Earth cools. Conditions at the boundary between liquid and solid have changed as the composition of the outer core evolves and as heat is lost to the mantle. The earliest inner core may have formed under different conditions from those that exist today. If the structure or composition has changed over time, different regions of the inner core might preserve different physical states. Some parts may be more ordered, others may be more dynamic. Observations that suggest layering or variation within the inner core could reflect this long history. So the deepest region of Earth brings together all the themes of the journey inward. Pressure increases to its highest levels. Temperature remains extreme. Composition becomes subtle and uncertain. Structure is no longer simple. The inner core is solid, yet it may not be a simple rigid metal. It may include regions where light elements move within a stable iron framework, creating a state that shares properties of both solid and fluid. This possibility does not overturn the basic picture of a solid center. It refines it, suggesting that solidity at such depth may include behaviors not seen at the surface. Observations indicate a solid inner core with anisotropy, structural variation, and an outer region that may be less rigid than expected. Experiments and simulations indicate that iron alloys under these conditions can adopt complex crystal structures and may allow significant mobility of lighter elements. It remains uncertain whether these lines of evidence converge on a fully supersonic state within Earth, or whether a range of more conventional explanations will account for the observations. What is clear is that the inner core challenges simple categories. At the center of the planet, matter exists under conditions that push the boundaries of known behavior. The journey inward ends with this uncertainty. The surface shows motion and change. The mantle shows solid rock that flows. The core shows liquid metal that moves and generates a magnetic field. The inner core shows solid metal under pressure, structured, anisotropic, and possibly hosting unusual states of matter. At the deepest point, the planet does not become simpler, it becomes more subtle. The center of Earth is not a quiet end. It is a place where physics itself must stretch to describe what exists there. The center of Earth remains out of reach, but not beyond patient understanding. From the calm ground at the surface to the compressed metal at the core, each deeper region changes the meaning of familiar words. Rock becomes something that can flow without melting. Pressure becomes strong enough to reorganize crystals into denser forms. Heat rises through the mantle in motion so slow that only their effects can be seen. Metal gathers below, first as a moving liquid that sustains the magnetic field, then as a solid center shaped by forces that have no surface equivalent. At every depth, the planet reveals that simple categories are only surface habits. Solid does not always mean rigid. Liquid does not always mean free from structure. Even the deepest iron-rich core may hold behavior that lies between the old boundaries of matter, with order in one part and motion in another. Observations indicate this possibility. It remains uncertain how far that possibility extends, and whether a superionic state truly exists within Earth today. Yet the search itself follows the same steady path as the descent. Each layer is understood through the evidence it leaves behind. Each boundary is traced by waves, heat, density, and change. So the hidden planet below the feet is not a stack of silent shells. It is a connected interior where the surface depends on the deep, where the magnetic field begins in unseen motion, and where the solid center may still hold a kind of internal restlessness. The journey inward comes to rest there, in darkness under immense weight, where matter endures in forms the surface never teaches, and where Earth keeps its deepest structure folded inside itself, quiet and unresolved.